In this video, we discuss the Wronskian. This is a construct for investigating linear independence of functions. In our current setting, it has somewhat limited utility. It is normally obvious when two functions are constant multiples of each other without dragging in the Wronskian. However, this material will later generalize to higher order cases where independence is harder to determine. The Wronskian of two functions is W of f comma g equals f g prime minus g f prime. Again, that's the Wronskian. We also use this vertical bar notation if you have taken linear algebra already. This may seem very familiar because the Wronskian is a determinant. If you don't know what that means, don't worry about it. Theorem. If f and g are differentiable, and their Wronskian is ever non-zero, then f and g are linearly independent. For example, let f be the sine of x and g be the cosine of x. Then w of f comma g equals the sine of x times the negative sine of x minus the cosine of x times the cosine of x, or negative sine squared x minus cosine squared of x. If this is ever non-zero, then the sine and the cosine are independent. At x equals 0, this is -1. So these functions are indeed independent. What if the Wronskian is always 0? That doesn't have to mean that f and g are dependent. The converse of the theorem we looked at is not true in general. However, in our setting, it does. Theorem. If f and g are solutions to a second order linear homogeneous differential equation, and W of f comma g equals 0 anywhere, then W of f comma g is in fact identically equal to 0, and f and g are linearly dependent. The Wronskian is a largely theoretical tool at this point, and we will not make heavy use of it. We will generalize it to higher order differential equations, where it is perhaps more useful, but not until chapter 5.